Welcome back to the deep dive. We're continuing our journey through the online encyclopedia of integer sequences, the OEIS. We're digging into some really interesting sequences, connecting them to the wider landscape of number theory. Hopefully useful for you students really getting into the field.
That's right. And for this particular deep dive, we've gathered quite a bit of material. We have the OEIS entry itself for sequence A080234, but also some, foundational historical papers and even some recent research. It all comes together to show how this one sequence touches on some pretty surprising areas.
Yeah, so our mission today is to really unpack A080234. It's listed as partitions into non-integral powers. We want to figure out, okay, what does that actually mean? Where did it come from? And then how does it connect to these other fascinating, maybe even slightly counterintuitive ways people generalize partitions in counting based on the sources we have?
Exactly. It's actually a perfect example, I think, of how a sequence that looks maybe a little niche at first glance can lead you down paths connecting to physics, of all things, and some really deep analytic techniques in number theory.
Okay, let's dive right in then. A000234. The OEIS entry, authored by Neil Sloan himself, defines it as counting the number of solutions to a specific inequality.
Right. The inequality is the sum of psi raised to the power of 23 for I equals 1, 2, and so on. That sum must be less than or equal to n.
Okay, sum I equals n. But there are rules for the talks, aren't there?
Yes, crucial rules. The dog's values themselves have to be integers, and they have to form a non-decreasing list starting from 1. So 1 equals by 1, by 2 equals by 3, and so on.
A non-decreasing integer.
And the list has to have at least one term by 1, but it can't have more than n terms in total.
Right. So this is quite different from the standard partition function, PAN, where you're just summing integers to get exactly n. Here, the bases are integers, but you raise them to this non-integral power, 23, and you're counting lists where the sum of those results stays below or equal to n.
Precisely. That's the key difference. You're not partitioning directly. You're counting the allowed lists of integer bases SI whose transformed values, psi of 23, sum up correctly according to the inequality. It's a subtle but important distinction.
Okay. The OEIS entry gives the first few terms, 1, 3, 8, 18, 37. Let's maybe look at that example for A3 equals 8. How do we get 8 solutions?
Yeah, that example really helps clarify things. We need some psi alias 3. Let's break it down by the number of terms in the list by 1 by 2.
Okay, one term first.
Right. If we have just one term up by 1, we need by 123, AO3. Since by 1 must be an integer, by 1 we just check. 123 is 1. That's less than or equal to 3. So 1, 1 is one solution. 223 is about 1.587, still 3. So by 1, 2 is another. 323 is about 2.08, still good. By 1, 3, 423 is about 2.52, still good. By 1, 4, 523 is about 2.92, still good. By 1, 5.
Almost there.
Yeah, but 623 is about 3.30. That's greater than 3. So we stop. The single-term solutions correspond to the bases 1, 2, 3, 4, and 5. That's 5 solutions right there.
Okay, 5 down, 3 to go. What about two terms? The list is by 1 by 2, with 1 by 1 it is by 2.
Right, we need 123 plus by 2, 23 equals 3. Let's try starting with the smallest possible by 1, which is 1. If by 1 was 1, the inequality becomes 123 plus by 223 equals 3, or 1 plus by 223. That simplifies to by 223 equals 2.
And by 2 must be greater than or equal to by 1, so by 2 equals 1.
Exactly. So which integers by 2 equals by 2? S plus 1 satisfied by 223 equals 2. Well, by 2 it's 1 works. 123 equals 1 is 2. So the list 1, 1 is the solution. Its sum is 1 plus 1, 2. By 2 equals 2 works. 223 is about 1.587, which is equals 2. So the list 1, 2 is another solution. Its sum is about 1 plus 1.587, which is greater than 2. So no more solutions when in 1, 1, 1.
Okay, so 1 and 2. Are there any others? What if by 1 is bigger than 1?
Let's try by 1 equals 2. We need 223 plus by 223. We know 223 is about 1.587. So 1.587 plus by 223, that means by 223. That means by 223 equals to 1.583, which is about 1.413.
And we need by 2 by 1, so by 2 equals 2.
Right. Is there any integer by 2 equals 2 such that by 223 is less than or equal to 1.413? Well, no, even 223 itself is already too big, 1.587. So no solutions start with ECA 1, 2 or anything larger.
Ah, I see. So the only two term solutions are 1 and 1 and 1 and 1, 2. That makes 2 solutions.
Correct. So 5 single term plus 2 two-term, that's 7. We need 1 more.
Must be a 3-term solution then. By 1, by 2, by 3, with 1, by 1, by 2 equals by 3.
Yes. We need like 123 plus by 223 plus by 323. The smallest possible value for each SI is 1. So 123, 1. What if 8, 1 by 2, 1 by 3, 1? The sum is 1 plus 1 plus 1 plus 1 to 3. Is that 3? Yes, it is. So 1, 1, 1 is our 8th solution.
Can there be any others with 3 terms?
Well, if we tried to increase any of the SHA values, say by 1, 1 by 2, 1 by 3, 2, the sum becomes 1 plus 1 plus 223, which is 2 plus 1.5 87, clearly bigger than 3. Any other combination will also be too large.
Just 1, 1, 1, 1.
Just 1, 1, 1. And that gives us our total. 5 plus 2 plus 1 equals 8 solutions for A3.
Got it. That makes the definition concrete, but it still feels, well, a bit arbitrary. Why 23? Where did this specific way of counting come from?
Now that's where the story gets really interesting. We turn to that Agarwala and Aulick paper from 1951. It provides crucial historical context. See, the study of partitions, going back to Euler and then Hardy and Ramanujan, it started as pure number theory.
Right, just counting ways to break up integers?
Yeah, exactly. But then, around the mid-20th century, physicists and mathematicians started realizing that the mathematics of partitions was actually incredibly relevant to problems in physics, specifically statistical mechanics.
Statistical mechanics, like thermodynamics, dealing with large systems of particles.
Precisely. Think about atoms, molecules, energy levels. The Agarwala and Aulick paper mentions work by Bohr and Kalkar, who were pioneers in using partition theory to estimate something quite physical: the density of energy levels in heavy atomic nuclei.
How does that work? How do integer partitions relate to energy levels?
Well, in quantum mechanics, energy often comes in discrete packets or levels. So if you have a total amount of energy in a system, like a nucleus, the number of ways you can distribute that energy among the available levels or components, that looks a lot like partitioning an integer. Counting the partitions gives you a way to estimate the number of possible states, the density of states.
I see. So the mathematical structure fit the physical problem.
It did. And this sort of physical approach, as they called it, led researchers like Aulick and Kothari to explore the connection further. They started looking at statistical systems, or assemblies, that naturally corresponded to known partition functions. And then they asked the natural next question: what if we generalize partitions? What if the parts, or the rules for combining them, aren't just simple integer sums?
And that's where the non-integral powers came in.
That's exactly where Agarwala and Aulick identified this specific generalization partitions into non-integral powers of integers as an interesting extension arising from thinking about these physical models. The 23 power wasn't just plucked randomly. It likely emerged from exploring generalized physical systems where energy distributions might follow such power laws.
Wow. So A080234, this specific sequence, has roots in trying to model physical phenomena using generalized partition ideas. That's unexpected.
It really is. It's a fantastic example of that interplay between physics and pure mathematics. A question motivated by physics leads to a new mathematical definition and a new integer sequence.
Okay, that explains the origin. Now, the other sources we looked at also talk about fractional or non-integral ideas related to partitions, but they seem to define them very differently. It really shows how many ways you can generalize a concept.
It certainly does. Let's take the Iskander, Jain, and Talvola paper. They introduce something they call fractional partition functions, palfa, where alpha is a rational number.
Okay, palfan. How is that defined? Is it like A000-234?
Not at all, actually. Their definition is purely analytic, based on generating functions. Remember, the generating function for the standard partition function, PNN, is the infinite product 1xk and x1.
Yeah, where the exponent is max of 1, corresponding to alpha 1 exactly.
Iskander, Jain, and Talvola define palfan as the coefficient of xn in the series expansion of product 1xk, alpha. So the fractional part comes from the exponent alpha in the generating function itself, not from raising the bases icky into a fractional power, like in A000234.
Ah, okay. So two very different ways to bring fractions into partitions. One changes the terms being summed, A000234. The other changes the structure of the generating function, palfan.
Precisely. It's a completely different mathematical object, even though the terminology sounds similar.
And that paper managed some pretty impressive results for these palfan, right? Using complex analysis.
Yes, very impressive. They applied the Rademacher circle method. For the students listening, this is a seriously powerful tool from complex analysis. It essentially uses integration along paths in the complex plane to precisely extract coefficients, like Pn, or in this case palfan, from their generating functions.
It kind of fishes out the exact value.
That's a good way to put it. It's particularly good at handling the behavior of the function near points where it might blow up or become difficult, the singularities on the unit circle. They adapted this method, originally perfected for Pn, to get an exact formula for palfan when alpha is rational. That's their theorem 1.1.
An exact formula. That's amazing.
It is. They also figured out the asymptotic behavior, how palfan grows as n gets large. But interestingly, the paper notes that even with this exact formula, there isn't necessarily a simple combinatorial interpretation for palfan, for just any rational alpha.
Meaning we know the formula to calculate it, but we don't always know what simple things it's counting. Unlike A000234, which counts those lists of bases 11.
Exactly. For Palfin, the definition is analytic via the generating function. Its combinatorial meaning, what it counts in terms of objects, can be quite elusive for general alpha.
Fascinating. Okay, so we have generalizing the bases, AI000234, generalizing the generating function, Palfin. And then there's the Zeilberger paper, which introduces another twist on fractional.
Yes. Doran Noam Zeilberger's paper offers a third perspective. They talk about fractional counting of standard integer partitions. They define a quantity, Bn.
Bn, what does that count?
Well, it doesn't just count each partition as one. Instead, it assigns a weight to each partition of M.
A weight? How is the weight determined?
The weight for a given partition, say n equals lambda 1 plus lambda 2 plus b plus lambda, is the reciprocal of the product of its parts. 1 lambda 2 plus lambda.
Okay, so you take a partition, multiply all its parts together, and take 1 over that product.
Right, and then Bn is the sum of these weights over all possible integer partitions of n.
Let's try that N of 4 example again. The partitions were 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Weight for 4 is 14. Weight for 3 plus 1 is 131 equals 13. Weight for 2 plus 2 is 122 equals 14. Weight for 2 plus 1 plus 1 is 1211 able. Weight for 1 plus 1 plus 1 plus 1 is 111 equals 1. So B4 is 14 plus 13 plus 14 plus 12 plus 1. Let's see. Common denominator 12. 312 plus 412 plus 312 plus 612 plus 2212, which simplifies to 73.
Perfect. So B4 equals 73. Notice how each partition contributes a potentially fractional amount to the total Bn. Here, the fractional aspect isn't in the parts or the generating function exponent, but in the counting measure itself.
So 3 distinct ideas, all using fractional or non-integral language. That's really useful to distinguish. Now, the Zeilbergers noticed something numerically interesting about BNN, didn't they?
They did. They looked at the ratio BNN as n got larger and larger, and it seemed to be settling down, approaching a specific limit. Their question 1 in the paper was essentially, what is that limit? It's a classic case of computation hinting at a deeper pattern.
And the answer is quite elegant, connecting to a fundamental constant.
Incredibly elegant. The limit, as n goes to infinity, of Bnn turns out to be e raised to the power of negative gamma, where gamma is the Euler-Mascheroni constant.
E gamma.
Yeah. And fascinatingly, this result wasn't entirely new. D.H. Lamer had apparently found it back in 1972, and it was later rediscovered by Will Salwin and Fernando Chamizo. It's just stunning that this specific way of weighting partitions connects to E and gamma.
Truly unexpected. Did they have other questions or results in that paper?
They posed a question, too, about a related function satisfying a differential equation, which the source notes was solved by Christopher Reiba. And they also briefly mentioned that this idea of weighted counting isn't limited to partitions. You could apply similar ideas to counting permutations or set partitions with different weights. It's a broader technique.
Okay, so we've journeyed from 000234, changing the Bessesum rule, to the Palfin rule, changing the generating function, to Bn, changing the counting weight. And you mentioned there's also work on partitions with specific complex constraints.
Absolutely. The field is vast. The Andrews, Bringman, and Malberg paper is a good example. They look at very specific types of partitions, like Schur partitions or Gulnitz partitions, which have quite intricate rules about which parts are allowed and how they must differ from each other.
So not fractional, but highly constrained.
Right. And studying these constrained partitions often requires its own set of sophisticated tools, things like modular diagrams, which are visual aids, or Q difference equations, which are like differential equations but involve functions evaluated at Qx and x. They use these tools to find new ways to represent the generating functions for these special partition types. It just shows the diversity of techniques needed across partition theory.
Okay, let's try to step back and connect these threads. We started with FS000234, saw its physics link, explored these different fractional ideas. How does this all fit into the bigger picture of number theory? The Science News article seems relevant here, especially bringing Ramanujan back in.
Yes, that article provides excellent context. It reminds us of Ramanujan's incredible, almost mystical discoveries about the standard partition function, Pn, those congruences, like P5n plus 4, always being divisible by 5, or P7n plus 5 by 7. For a long time, these looked like beautiful but isolated arithmetic quirks.
They seemed too neat to be coincidences, but hard to explain systematically.
Exactly. But then, as the article highlights, came Ken Ono's major breakthrough. Building on earlier work, Ono proved that there are actually infinitely many such congruences,
Yeah.
holding for all prime numbers.
Infinitely many. How?
By uncovering a deep structural connection between partition numbers and the theory of modular forms.
Modular forms again. These are the really sophisticated functions with amazing symmetries connected to things like Fermat's last theorem, right?
The very same. Modular forms are absolutely central to modern number theory. They appear in relation to the Riemann hypothesis, the Langland's program. Really deep stuff. Ono's work showed that the sequence Pn, which seemed on the surface just to be about counting ways to add integers, somehow encodes the intricate symmetric properties of these powerful modular forms. It's like finding hidden order and structure beneath apparent randomness.
So studying partitions, even these generalized or weighted versions like A0000234 or Bn, isn't just some niche combinatorial exercise. It can actually tap into these fundamental structures.
That's the crucial point this Science News article makes. These partition-related concepts, sequences, and functions are not just mathematical curiosities. They can be, and often are, a testing ground for developing new mathematical tools, for exploring deep conjectures, and for illuminating surprising links between different mathematical fields. Thinking about partitions differently, like A000234 does, can lead you straight to the frontiers of research.
Okay, so let's try to summarize this journey. We started with A000234, defined by this inequality with bases to the 23 power.
We found its surprising origin in statistical physics from the 1950s.
Then we saw how the idea of non-integral or fractional partitions gets interpreted in completely different ways, changing the generating function's exponent with palfan, or changing the counting weight itself with b on n.
Right, and exploring these variations requires, or reveals connections to, some pretty advanced mathematics, the Rademacher-Circle method, Q-difference equations, and ultimately the profound theory of modular forms underlying even the basic partition function pi and f.
It really underscores how applying analytical tools to these combinatorial questions and just asking, what if we tweak the rules, can lead to really deep insights.
Absolutely. It shows the interconnectedness and the richness that can emerge from seemingly simple starting points in number theory.
It definitely makes you think. If this one sequence, A000234, born from physics, connects outwards like this, what other stories are hidden within the millions of sequences in the OEIS? What other unexpected bridges between different areas of mathematics are just waiting to be uncovered by the next deep dive?
It's a landscape full of potential discoveries. Always more questions to ask.
Indeed. Well, that brings us to the end of this particular deep dive into OEIS A000234 and its fascinating neighborhood in number theory. We hope exploring these connections has been as insightful for you as it has been for us.